Hello, everyone. Welcome to recent advancements in container isolation. I think we're going to get started. So, hi, my name is Tim Allclair. I'm a software engineer at Google, and I'm also co-chair of Kubernetes SIG Auth and a member of the product security team.
And I'm Adin Scannell. I'm also a software engineer at Google, and I work on gvisor.
So today we're going to talk to you about container isolation, but before we dive into that, I want to make sure we're all on the same page about what we're actually talking about when we say isolation. A model of security that I really like is the confidentiality, integrity, and availability model, or CIA model. These are three key properties that we want to maintain across any isolation boundary. But there's two other properties that I want to call out. The first is that isolation is really a multi-dimensional problem. It's not enough to just isolate the network when an attacker can potentially escalate privileges through unsecured syscalls and then attack the network from a different angle. And security really requires a holistic approach. The second property to call out is that isolation is a directional problem. Just because a container is well hardened and the node is isolated from processes in that container doesn't mean the inverse is true. A process running as root on the node, for instance, the kubelet, can easily reach into that container, read its data, and use its credentials, that sort of thing. So with that, I'll hand it off to Adin to tell you a story.
So we're going to tell a story to help frame some of these ideas in more concrete terms. And we're going to tell the story with the help of a little bit of time travel. So everyone arriving late might be really confused, but that's OK. Everyone here will know what's going on. So almost no one knows this about me, but I don't really care about containers. My true passion is actually meme-based cryptocurrency. And in 2019, Tim and I both leave Google to start an online Meowcoin exchange. Now, everyone knows that the past few years have been rough for cryptocurrency generally, but Meowcoin just takes off like a rocket. Unfortunately, our success is rather short-lived, and we're back here in 2020 to present a retrospective of the great Meowcoin theft.
So our story starts with an attacker, Eve, who manages to penetrate our clusters. The way she does this is by hiding a backdoor in the popular NPM library dclod. We made heavy use of this library in our memes service, which attaches a meme to every Meowcoin transaction. And Eve exploited the backdoor to gain a foothold into our cluster in the memes prod pod. So we start here. Eve has code execution in memes prod. And the very first thing she is going to do is attack the API server because she knows she can get full access to the cluster from there. Fortunately, we're using best practices, and since memes prod doesn't need to talk to the API server, we haven't even mounted a service account credential into memes prod. So that's a dead end. Next, she goes after the Meow wallet, where the goods are. Fortunately, we're using Istio to implement a least privilege model of network access. We use fine-grained authorization policies through Istio. Istio is 1.0 since 2018, as I'm sure you all know. And we're not going to say too much more about this here, but there's an entire track on service meshes on Thursday, and I encourage you to check it out if you're interested in this topic.
So here's where we got a little bit lucky. We were running our memes prod service inside a sandbox. And the reason is that it's exposed to the public internet, and we use every random dependency we can find from every corner of GitHub. So we decided it would be prudent to keep it inside a sandbox. So Eve was not able to escalate directly. Now, the reason you might use a sandbox is that you want to mitigate the risk of a kernel vulnerability if there's a high chance of running potentially malicious code inside that container. And this may be running user code directly, or it may be some front end that you feel there's a high chance it's exploited, or you're running some media transcoder, or operating on some other potentially malicious user input, or maybe just like us, you have a big pile of third-party dependencies that you don't necessarily trust or can't audit. So the way a sandbox can add protection depends on the type of sandbox. Since this is a very hot topic, we're going to be talking about a few different variants. In general, when you run an application or a container, they're interacting directly with a fairly broad, complex kernel surface. And the whole point of a sandbox is that you want to either transform, limit, or somehow insert an additional boundary in this layer to prevent or mitigate the risk of kernel vulnerabilities leading to privilege escalations. So just to reinforce this a little bit, this table shows a list of Linux kernel vulnerabilities, actually code execution vulnerabilities published in 2017. And this isn't to rag on the kernel at all. Kernel is an incredible piece of software, but it's enormously complex and has a broad range of responsibilities. So with any large, complex piece of software, there's bound to be bugs people can exploit, including the sandbox layers that I'll talk about. And you just want additional boundaries, additional layers of defense. So the first thing to consider is that the host kernel itself has a bunch of mechanisms built in for limiting that surface. So you have things like the seccomp BPF policy for filtering system calls or LSM modules. And these are fantastically useful, and you should use it as part of your security best practice, even for applications you trust. Because they're very, very high performance, very, very low overhead, and they don't really change the semantics of the container at all. The one challenge with using these for sort of arbitrary workloads is that there's a fundamental trade-off between the degree of restrictiveness with these policies, so the degree you can lock down that kernel surface, and the diversity of workloads that you can run. So it's not necessarily feasible to take an arbitrary container that you know nothing about and run it using a very restrictive seccomp policy. So that leads to the first class of sandbox that I'll talk about, which is machine virtualization. The idea here is you take a container or a pod and you put that in its own VM. So VMs are fantastic, mature technology. On bare metal, you typically have very good performance now. There's a stream of sort of cloud-native hypervisors that are coming out that are focused on low overhead, fast boot times, no legacy stuff. But there's a couple of challenges with VMs in this model in general. The first is that there's a separate guest kernel inside this VMM that's generally talking physical cores and physical memory. And so you'll have a second scheduler, a second page cache, a second reclaim mechanism. And the degree to which that's a problem really depends on the kind of workload that you're running here. The second challenge is that hypervisors don't natively run containers, right? They run machine images. And so you need proxies and various plumbing and infrastructure to actually wire together containers that are running inside those VMs. And that's what projects like Kata containers are focused on doing. So the second category of sandbox that I'll talk about, I'm calling kernel virtualization. And the idea here is that the sandbox isn't talking directly to the kernel anymore, but it's talking to some other kernel interface. And you can do this for compatibility reasons. There's a couple of very famous examples. So LX Zones for SmartOS allows you to run Linux containers. Windows Subsystem for Linux, another great example where the application is obviously not talking directly to Windows, talking to some other component that is providing Linux ABI. Or you can do this for isolation, which is what gvisor is focused on doing. So at the bottom there is a diagram of how gvisor works. And it's effectively a second user kernel that is interpreting and implementing all of the application system calls. And it does that not talking physical cores and physical memory, but rather speaking threads and memory mappings. So it's trying to preserve the original container semantics, which makes it suitable for small, high-density services. It doesn't impose large, fixed overheads. And it has a very, very fast startup time. But this is a separate kernel implementation. It runs most things today, but it's evolving fast. There's some challenges around compatibility and performance, particularly for cases where we haven't really optimized for those things. So the last class of sandbox that I'll talk about, I'm going to call non-Linux environments. And I get asked about these a lot, so I thought it would be really useful to have a slide about them. But these are things that are not necessarily running containers. They're running different kinds of workloads. So a good example is Nabla containers, which is a runtime that runs Solo 5 unikernels. And these can be really efficient. They can expose a very, very small host system surface. But you're only able to run certain kinds of workloads that have been built for these environments. You're only able to run unikernels. You're not able to pull something off the shelf and run arbitrary Docker containers. The next thing, Isolate's Cloudflare had this famous blog post where they're talking about doing multi-tenancy using V8 and isolates. And this is very similar. You're running JavaScript and WebAssembly programs, and you're able to achieve high efficiency and performance, but it's not running containers, or what we normally talk about as containers. So all of these things are available. There's this new mechanism that you can use starting in Kubernetes 1.12 called the Runtime class. This allows you to define a distinct set of runtimes and then configure on a per pod basis which runtime to use. And there's a number of improvements that are landing, including accounting for sandbox overhead, being a bit smarter about how you can match features, how to know what can run with what, and of course a whole bunch of stability performance testing for the runtimes themselves.
So our sandbox successfully contained Eve and protected our kernel surface from her. However, we were running another memes service in our cluster, the memes dev service. Since this wasn't exposed to the internet, we hadn't bothered to sandbox it. But our Istio rules allowed for cross-communication between memes services, and so she was able to exploit the same backdoor and jump to memes dev, which is non-sandboxed. So from here, we'll talk a little about audit logging and how we were able to piece together this attack. So container ID back in 2018 was being actively discussed for extending the audit subsystem of Linux. This is actually the first native container concept in the kernel. What we think of containers as today are mostly pieced together through different features of Linux, and there's no kind of native container concept within there. So container ID adds that. It adds a way to tie audit events to a specific container. But Eve knew that we had a good audit system, so she decided to attack to try and obfuscate the logs by changing the system time. Thanks to the new time namespace that we were running in our super up-to-date kernel, when she changed the system time, it only changed the time within her container. We're also using best practices, even though we didn't have a full virtualized machine or kernel, we were still using various host kernel mechanisms to contain that container as well. So Docker enables an AppArmor profile by default on AppArmor-enabled nodes. But a new feature called policy namespaces, and with that policy stacking, lets us layer on an additional application-specific profile to harden that even more. So thanks to those improvements, she was only had a very small kernel surface exposed to her, but she attacked it anyway. Although we had a lot of vulnerabilities in 2017, we saw much fewer in 2019 and 2020, thanks to the Kernel Self-Protection Project. This is a project that aims to harden the kernel as opposed to adding new security features. And it's doing this through hardened C programming techniques, things that aren't necessarily new ideas, but are very difficult to apply to a project as complex and as old as the Linux kernel. So just to highlight a few improvements, the elimination of variable length arrays protects against stack exhaustion, type attacks, fixing bugs in switch statements through incorrect fall-throughs, initializing local variables, checking bounds, that sort of thing. Another improvement comes through control flow integrity. So back in, say, 2017, a buffer overflow attack would typically lead to an attacker writing some code onto the stack, and then changing the return address to jump to that address on the stack. From there, they've gained code execution. We fixed this by setting the stack and the heap to non-executable, since programs don't typically run code out of the stack. This led attackers to use a technique called return-oriented programming, where rather than writing the code directly to the stack, they would just modify the return addresses to call existing functions with arguments they control. And by chaining together those function calls, they effectively gain code execution again. That's what we fixed with control flow integrity. And two different mechanisms around this. One is to separate the call stack from the data stack. So a buffer overflow on the data stack, it would be hard to go from there to modifying the call stack itself. There's also some preliminary hardware support coming out through Intel's control flow enforcement technology and ARM's pointer authentication.
So everyone remembers 2018 was a rough year for many reasons, but one of those reasons was that we discovered that hardware doesn't really work the way we think it should work. And so Eve started scratching at the hardware to figure out if there were any secrets or credentials that she could steal from the node itself. And so as a quick background on how speculative execution works, is an attacker will try to trick the processor into executing down some path where it's accessing some data that they wouldn't normally be able to see. And this is a problem because it turns out that processors don't necessarily respect page table permission bits, bounds checks, or even EPT translations in the speculative path, which is very bad. And then on that same path, they use that data to generate some side effects in some shared architectural state that they can then observe once the processor realizes, oh, that's not the path that I'm taking, and unwinds that execution. They can still infer the original data that they wanted to get access to. So this could allow someone to steal credentials, keys, anything on that same host. Unfortunately, there was a lot of progress through 2018 and 2019 on this front, including a lot of software mitigations. So compilers have incorporated various fences to prevent the bounds check bypass specter variants. The kernel now has 2 sets of page tables to ensure that users don't have access to mappings that they shouldn't have access to. The kernel can be compiled with retpooling to ensure that user space can't poison branch targets or use steering to access gadgets that they want. And the kernel poisons physical addresses for page tables aren't present to defeat the foreshadow attack. And of course, there's no more lazy floating point, which is actually a performance gain anyways. So our main lesson here, we didn't actually take any action, but our main lesson was to keep all your kernels and tool chains up to date, because this stuff is continuing to land. There are also a number of hardware mitigations that landed in 2018, 2019. These include mechanisms, they're basically new control registers that allow the kernel to partition the branch target buffer to prevent using user values from the branch target buffer or values from a lower privilege level, allow it to flush that buffer on privilege transitions, and various things to prevent other kinds of attacks here. So the lesson here is also make sure you're keeping your firmware up to date, principally because the kernel will select the most appropriate mechanism to use, which could be some mix of hardware and software mitigations. So at this point, Eve was pretty frustrated, and she decided instead of trying to attack our service, she would just disrupt it by degrading the service and being a noisy neighbor. So software is rarely bound purely by cycles. It's usually bound by some other mix of different architectural components, like cache bandwidth, memory bandwidth. And so Eve, for example, just started running a random video transcoding service and chewing up all of the memory bandwidth available and degrading the performance of our memes prod service dramatically. So this is an active research area, particularly in light of the last things I just talked about. There's all these interesting side channels, and so people are looking at how to isolate all of these shared architectural components. But one thing you could try today is Intel RDT, which is available in recent kernels, and Run-C to impose limits on cache bandwidth and memory bandwidth and prevent the noisy neighbor problem. Unfortunately, we, like everyone else, were taken by surprise in 2019 when some security researchers discovered Impawsible Execution, and Eve was able to escalate privileges right to the node.
So this brings us to Chapter 3, Escalating Privileges. Eve has now gained code execution as root on the node, and we'll see what she can do from there. So the first thing is, now Eve has access to all of the credentials running on the node. This includes the kubelets credentials, as well as any other services that are running on that same node. So now she's going to go back to the API server. And let's take a look at a session log and see what exactly she did. So first, she uses the kubelets kubeconfig, which includes its credentials, to start making requests to the API server. She looks at the pods that are running, and here we see an abbreviated list of just the ones we care about. And now she's going to try and exec into that Meowcoin wallet. But fortunately, since the kubelet doesn't need to exec into pods, especially pods on other nodes, we forbid this through least privilege scoping on that. So she takes a closer look at the Meowcoin wallet and sees that it uses this wallet key secret. That sounds pretty juicy, so she tries to grab that secret. Fortunately, this is forbidden through something called the node authorizer, which has been in Kubernetes since 1.7. And what that does is it maintains a graph of all the resources that are required by all the pods that are running on a node. And so in this case, there weren't any pods running on node 1 that used the wallet key, and therefore node 1 has no business reading wallet key, and it can forbid it. But Eve has another trick up her sleeve. She says, what if I can coerce the wallet to be rescheduled onto node 1? So she takes a closer look at the wallet and sees that it's using a node affinity term to schedule the wallet workload onto a node that's labeled with a sensitivity of greater than 10. No problem, she says. I'll just patch node 1 to have that set that sensitivity to 11. But this is forbidden as of 1.13 because the node restriction.kubernetes.io label prefix is always forbidden. We're also going to work on kind of ramping up the number of labels that are forbidden as well. But so far, we've only been talking about using the kubelet credentials itself. One of the open areas going into 2019, or I guess we did this in 2019, is to apply these same restrictions to the daemon sets and the other workloads that might be running on the node, because those, if they need to, say, edit the node, then those workloads would be able to change those labels. So at this point, Eve is starting to get a little worried, and she wants to at least maintain persistence on this node. So she tries to leave a rootkit behind. Fortunately, we're using a container-specific image with a read-only root file system. And we've also protected the kernel via boot attestation to make sure a custom kernel or any unsigned kernel modules can't be loaded. But she has one other idea. There's this metrics pusher service running on node 1. And the metrics pusher receives metrics requests from other workloads in the cluster. In order to make sure that those other workloads are pushing metrics for themselves, it delegates authentication to the API server through token review. So in this case, the Meow wallet sends its service count token along with the request, and then metrics pusher delegates that authentication check to the API server. The problem is that metrics server now has a copy of the Meow wallet's service count credentials, and it can do anything that service count is capable of. Fortunately, we now have enhanced service counts, which add a few nice features. The first is expiration. So those tokens that are stolen can only be used for so long. Also, per pod information is attached to the service count. So from the audit logs, we can see exactly which pod or token was compromised. And most importantly, in this scenario, we have something called audiences. So with audiences, when Meow Wallet sends that request to metrics pusher, it's actually going to send a special token that's intended only to talk to metrics pusher and cryptographically signed, so that if Eve then uses that same token to try and talk to the API server will say, no, this isn't intended for me.
So at this point, we thought that Eve must have been pretty frustrated. She tried a lot of paths, been pretty successful, but she still did not have her claws on any of our Meow coins. So she took a step back and reconsidered her strategy. After a quick Google search, she actually found some credentials, admin credentials, for our cluster on one of our engineers' GitHub.files repos. So thankfully, none of that happened. And as far as I know, Meow coins are not a real thing. Maybe they are. But we were able to present and talk about a number of recent advancements in container isolation. These are in various degrees of development. The things in black and green are things that you can use today. The things that are yellow are things that you can use today but are moving fast and improving fast. And the things in red are stuff that will hopefully be usable in the near future.
So just to recap, at the beginning we talked about the multidimensionality of isolation. And here we saw a lot of examples about how our attacker was able to attack from all different angles and slowly kind of weave her way through the system. And so remember that it's really important to kind of consider every angle when trying to achieve secure isolation. And also we saw some examples of directionality where she was able to, once she had escalated to the node, access the credentials of other services running on that node. And there's one takeaway that we want to make sure we get across today, which is we talked about all of these really cool technologies that prevent all sorts of advanced attacks, but none of that matters at all if you don't get your basics right. And so kind of just to highlight 3 important ones, use best practices for credential management, don't post your admin password to GitHub, protect your network and services. This is something that I see for customers forgetting occasionally. You can isolate your container all you want, but if you have wide open services on the network, that doesn't matter. And finally, of course, keep everything up to date, patch, and patch some more. So thank you. I think we have a little time for questions if anyone has anything. The question is, can we talk about overheads for sandboxing? And the optimizations that have gone into it.
So did you mean one particular kind did you mean a specific kind of sandboxing or what? For gvisor? Sure, so I mean the different types of sandboxing are going to impose different kinds of overheads, so it's really hard to say one number for any given case. For example, I'm going to get to a specific answer to your question, but I'm just going to frame it first. The machine virtualization case, right, I mentioned it runs really efficiently on bare metal, right? But if you're running in a already virtualized environment, you want to carve things up, all of a sudden you don't have bare metal anymore, you're going to incur massive overhead from nested virtualization. And so that's a particular cost that you'll pay in that environment. For gvisor, there are really 2 specific kinds of overhead that you'll pay. One is for trapping, for intercepting the system calls from the application. It really depends on the underlying platform. So similarly, if you have bare metal and you can use like a KVM-based platform, you're doing hardware interception, that is not that high a cost. But if you're running virtualized, it's a much higher cost because you're using ptrace or some other interception mechanism. But again, it depends on the exact environmental constraints because it could still be faster than nested virtualization in many cases. The other kind of overhead for gvisor that I mentioned there is it's a separate kernel implementation. And so I said we haven't optimized for a lot of use cases yet. The static file serving and sort of big scalability use cases are 2 that I mentioned. And that's just really about the implementation itself, the implementation of the kernel and the sort of things that you've looked at, right? We've looked at sort of web application servers principally, where you're not trying to get as much static content out as you possibly can, and they're typically pretty small, right? We're focused on the scale to 0 problem versus the let's run 1 per enormous machine. And so there's a bunch of scalability work that we have to do. Does that answer your question at all? Maybe not. Or,
So the question is, Docker, the minimum kernel version for Docker is much older than what we consider a modern kernel. You can go pretty far back and still run Docker, and what are the chances of advancing that minimum requirement? I don't work on Docker directly, so I can't speak exactly for them, but I'm guessing that's more of a technical requirement. So if you run on that kernel, it will work. And it sounds like what you're asking about is more of a kind of a compliance thing to say, to comply with whatever standard, we want a minimum kernel version. That sounds reasonable, but I don't know off the top of my head what's happening in that area. Yeah, so the question is about isolation of storage. So we didn't touch on that too much today because this is really an active research area and we don't know exactly what the plans are here. But you may remember the symlink vulnerability that we talked about, what was it, last year, the end of last year, I think? Or I guess the beginning of this year, we came out with the patch for it. There's actually a session, I can't remember exactly when it is, but talking about that vulnerability and the fixes to it, if you're interested. Just search for symlink on the schedule.
I think it was this morning.
Oh, it was this morning? Uh-oh. Sorry. But so we patched that vulnerability by checking very manually for symlinks when volumes are mounted. But that's a very kind of specific fix for that one issue. And even if you're using sandboxes, the way we do it today is we basically mount that volume on the host and then sort of pass it through to the sandbox through basically, the sandbox's equivalent of a bind mount. And this means that it's actually exposed to the same types of vulnerabilities, and we really only have one security boundary there, but we want two for sandboxes. So we're starting to think about ways to maybe handle some of that mounting directly within the sandbox context, so it doesn't actually have to be mounted to the host. But as I mentioned, these are kind of like an open research area that we'll be looking into more in 2019.
So you talk about keeping your kernel as up to date as possible. What is like minimum support level of kernel up-to-dateness? Running like those leading edge, or is there like a read inside?
So, I mean, every distribution carries security patches, right? And you want to just make sure that you're using a distribution that you trust to patch appropriately and up to date on all of those trees, right? Like, I don't think there's a general answer to, version X is going to fix all your problems. But it's a very, very, very important best practice. That's the point I wanted to hammer home on that one.
For container service accounts, it is a big, or like if you have in one top multiple containers and you want to give access to one of those service accounts?
Yeah, so the question is, can we give access to multiple service accounts from one container? The technical answer is yes, if you are willing to manage those service accounts yourself. A basic way that you could do that is to give permission to the main service account that you're attaching to the pod to act as or impersonate the other accounts. You can also manually mount those service account tokens into the pod, assuming it's running in the same namespace. But also, I would kind of caveat that with once we have audiences for service accounts, hopefully the need for that, for having multiple accounts isn't as high. I think we're just about out of time, but I'll stick around outside if you have any more questions.